Pessoal, primeiro, obrigado.
Hello, everybody. Can you hear me? I hope so. Very excited to be here at Besides Brazil. I'm very fond of Besides. Did some presentation in the other Besides events, so very excited to be here as well. I'm Vera Mens, a vulnerability researcher at Team82, and today we are going to talk about a very cool research that I did, and I hope you will enjoy the talk, at least as much I enjoyed doing this research. So today's title is How We Hacked a 100,000 gas chromatograph and without having it, and how you can do it. So let's start. Prior to talking about the research, I would like to introduce myself. I'm Vera Mens. I'm a vulnerability researcher at Team82 by Claroty. You're probably familiar with the team, and if you are not, we are the teams that performing a lot of vulnerability research on OT and IoT devices. And our goal is to find vulnerabilities and disclose them to the vendors so they could be patched. And after the vendors patched the vulnerabilities, we are going to talk about them in a presentation like this one, or publishing a blog about it. So we would like to the community to be better at security and be more aware of the vulnerabilities. Of course, our goal is also to disclose those vulnerabilities and make them patched. As for me, I mostly do embedded devices because this is what I most enjoy doing. And me and my team also participate in Ponton competition, which is a very cool hacking competition. If you are not aware about it, you are welcome to read. So let's start about the research, but prior we need to get some context for the device we are going to talk about today. So we are going to talk about gas chromatography. We are not going to get deep dive into how it's work. It's not our business here, but we want to just understand what it does. And it mainly its goal is to take a mixture of gas into some oven and output the discrete components in its gas. So it's used in chemistry and pharmacy and some other industries. And as for us, a vulnerability researcher is just a computer that we can hack and exploit. So this is what interests for us. And as for me, I'm not aware of what a gas chromatograph is, right? I'm a security researcher. I'm not a chemist or in any way. So for me, the first thing I need to do is read the whole documentation to get the context for this research as well. Uh, we Today we are going to talk about the research and how it's all started. It's all started when my boss asked me to perform an analysis on proprietary protocol as it works with this device. This gas chromatograph, like something that I never heard of before, and we saw right now what it do, and this is how it looks like. And the specific gas chromatograph that we are going to talk about today is Emerson Rosemount uh, gas chromatograph that is somewhat one of the smallest models that they have, but it's still pretty big in size. Um, I don't have the device. This is in the title, but I would like you to look just for a second in the internals, just to get impression on how it works. Along with the device, there is a software client which operator will install on his Windows computer, and with this client, we can monitor the device, configure it, and maybe see some logs, right? For almost any physical device that we have, we are often have some uh, clients that we can install on our computer, so we can be able to configure it. So this is our ecosystem here in this research. Just a second. So let's look at it in high level. We have our lab technicians that sitting in their labs, and they installed the configuration program on their Windows machine, and we have the actual lab in which we have the actual gas chromatograph device, and we have a protocol, in this case, a proprietary protocol that was developed by Emerson. And that protocol is a secure protocol, it's encrypted, and it runs on a TCP port 10,000. And with this protocol, the technician will communicate with the device via the configuration program, of course, uh, see some logs, and perform any operation that industry needs to perform. So this is how this setup looks like in real world, of course. So our goal here, and it's how this research even started, is to analyze the proprietary protocol. As it with many proprietary protocols, this protocol is not documented. So when we need to analyze the protocols that we are that communicates between the program and the device, the only way that we have and can to be able to understand the protocol, we need to somehow to emulate or simulate this environment in our lab. And the optimal prerequirement for protocol research are that we will have the client software, and we have the device, and the capability to see and even alter the network and the communication between the two. If we are able to see what's going on, and we have the actual program and the device, we can reverse engineer all of the components, and somehow with time and many effort to understand what is going on. And it takes time, of course, because it's a non-documented protocol, so we have to be very patient. So the one thing that's very easy to acquire, of course, is the software client. It can be downloaded from the website, and it is easy download. Can be easily downloaded and installed on any Windows machine, and we can already start with understanding the basic capabilities of the device. And that's what we did. It is a easy step, nothing too complicated is happened here. Um, but we don't have the actual device, and we somehow need to emulate it. And let's see why we don't have the actual device. The thing is that those devices are pretty expensive, and as you can see, the price here, it's a little bit bigger than I'm allowed to spend on my research. And since we couldn't just buy this for a 2 weeks research, we decided to emulate it. And we before we starting to emulate the device, we need to understand what we want to emulate, right? Because we have the actual device, what it performs, it gets a mixture of gas and gives some components about discrete components about its mixture. But we don't need that, right? We don't care about its chemical components and the abilities. We care about the operating system and the main binary that operates the proprietary protocol. And for that, we only need the firmware. We don't need the actual device. And luckily for us, Emerson published its firmware on its website. So we just can download it and extract it. And luckily for us, it was a Linux file system, right? We all are familiar with Linux file system. It quite easy uh, to take some binaries out of it and maybe try to run it on another machine, right? So uh, when we see a Linux file system, it tells us that we are probably will be able to successfully emulate the protocol and connect to the software client. But we need in this phase we need to understand what a binary we need to emulate, right? We need to find a binary that implements a protocol, and it's not that easy or straightforward because we have the device that is developed in some in at Emerson, right? And it's packed only with the binaries and a structure it's needed to operate in specific industry. It's not a general computer when I can Google where a specific file resides, right? Um, in this phase, this is quite tricky phase in which we need to find the actual binary that implements the protocols that we want to analyze. And it is good practice to start to find this binary in these files, because and in Linux, and especially in a not general purpose machine, the first binaries that need to be always operated, it will be reside in init files. So after a lot of searching, we did find it, and its name doesn't look like any something interesting, but this is uh, this is how it looks like. We find the init script that inits the file that init from the start of the file system, and in one of the scripts we see uh, the actual binary is executed. The name of the binary is XTPD, nothing that can somehow hint us that it is the main binary that will implement the protocol. But after some errors, and we are able to find it. Another, sorry, I'm trying to. Is there some problem? the next slide it's not, I'm not sure that I'm getting it. Yeah, just a second. I'm not sure that we see the correct slide. I will just wait for a second. Oh yeah, that's cool. That helps. Thank you. Yeah, that's cool. So the question we are about to ask here is, can we analyze the protocol statically without emulating the protocol? We have the binary, right? We can reverse engineer it, put it in IDA, and just see how it behaves. Um, Technically, we can do it, of course. I have a technical problem here because it seems like I push forward the slide, but it's not working. Maybe someone can help me. Yeah, I see that. I can. I. Yeah. Okay. Okay. Now we are good. Yeah. Cool. So the answer is yes. Theoretically, we can reverse engineer the binary and find out how the protocol works. If it's matter of time, right? But eventually, all the code that implements all logic is within the binary. And by sitting on the binary for hours and hours, reverse engineer it, we are able to get the full logic. And it's in some project of ours, it's the only way to go. In case that sometimes not every device can be emulated, and some devices are have to be researched statically, and that's what we do. So theoretically, yes, it's possible, but we rather have the emulation working, so we will be able to manipulate the protocol to see how it works, so will be able to fully analyze it, which will take a lot of a lot of less time if we will do it dynamically and not statically. So the next question is how we perform that emulation. So let's go back for a second in for our context, right? Our goal in this research in that phase is to analyze the proprietary protocol of gas chromatograph that we cannot buy. We cannot buy it because it's super expensive for our research, and we have no other option to go other than emulate it. And the emulation is possible because we have the firmware on Emerson website, which is not encrypted and can be easily extracted. We have downloaded the firmware and we have extracted it and found the main binary that implements the proprietary protocol. Now the situation that we have is that we have the Microsoft client that we have downloaded from the website, and we have the firmware. We found the main binary that implements the communication between the client and the device. And now we are in the phase that want to emulate the wall settings, the wall setup, so we will be able to see this communication in action. So how do we emulate this? As I told before, we saw that the firmware is basically a Linux file system, which is very convenient for us in the case of emulation. Because we know that we can now be set some Linux machine, right? We can copy the firmware file into it and perform sage root command. We will talk about it later. But first, let's see some caveats that we have. The thing is that most of the OT and IoT devices comes in non-standard architecture. For in this specific case, the architecture is PowerPC. It's not that common to have in general purpose computers. So if I would like to put it in some Ubuntu, I will need to find the computer that runs PowerPC, which will be quite challenging for me. For ARM today, we have a lot of options, right? We have a Raspberry Pi, and we have even the Apple that uses ARM as its architecture. But for PowerPC and MIPS, it's still a challenge. And for this specific emulation, we will need to use a QEMU. For those who doesn't know what QEMU is just an emulator that you can install on your host machine, general computer, whatever, or any other, and it will run instructions from another different architecture, which is super useful for OT and IoT research. In my case, I have my Mac on which I have Ubuntu. I have an Intel Mac, and I have Intel Ubuntu on it as virtual machine. And on top of this, I have QEMU that will run the the machine that will run the PowerPC instructions. So what we are going to do is we are going to install PowerPC Ubuntu with QEMU, and after we will power on that Ubuntu machine, we will copy the file system into it and route to the file system. So we will have the file system of the gas chromatograph working for our emulation. Let's see how we did it. Okay, so this is the actual command I used when I powered the Ubuntu PowerPC. I'm just downloaded the Ubuntu PowerPC from Ubuntu website, and I searched for a board that will implement the machines that will implement the PowerPC architecture that will be supported by QEMU. This is an important part in emulation, and in my case, this machine was a Mac 99, which is a Macintosh, really old machine, which was on PowerPC. Yes, Macintosh back in the days used PowerPC architecture, and this board is supported on QEMU. So for in my case, I just run the Ubuntu on a Z board with QEMU, and after installation phase, I have an Ubuntu PowerPC installed with the emulator. So after some time, I have my setups going on. I have, you cannot see it, it's in a GIF that probably cannot be shown well, but here's the situation that I have my client that is installed on Windows machine, and I have the emulation, and it's all working, and it's all working. I mean, the basic startup of the communication is working, and I can start to investigate the protocol, or am I? After some time, and I understood that, and I said it earlier, that the protocol is encrypted, and uh, and now I need to wait to see somehow the communication. So that's the situation we are at now. We have the program, Windows program, the client, and we have the emulated device on the QEMU, and we have the communication channel, which is encrypted on TCP 10,000. We will have to patch the machine to disable the encryption, And in our case, we were really lucky because the the client supports, and the client and the device supports both encrypted and decrypted communication. So we all we needed to do is to lie about our version in is a handshake of it's a negotiation between the client and the server, and to have uh, our communication totally decrypted. So now we are at the phase that we can see what's going on. We have our client and we have our device and we have the communication that we can actually see what is going on between the two parties. And in this picture, we see the actual client, and we see here the Wireshark, the IDA, and the client, both for a couple of hours or maybe days, while I'm analyzing the protocol. So the protocol is rather simple one, and just a second. The protocol is very simple, and I would like just to cover it in its basics. So we have our header, which is some sequence number and command type and length of the data, and the data is just embedded on the bottom, right after the header. And just to illustrate how the protocol works, I will give an example of one of the commands, like see one of the commands to change level of a user that communicates between client and the device. So in this example, we have our header and we have our command type, which is 11 hex, like seen here, and we have the data length, and after that we have the actual username and the level we want to be changed to. So very simple protocol, nothing too complicated. Uh, the next phase in this research, after we have analyzed the protocol, uh, my team leader would like to know whether the protocol is secured. And this is a phase in which we start to look for vulnerabilities. Um, and let's find out if the protocol is secure, right? So we have here pre-authenticated remote code execution, and let's see how it works, how it was discovered, and you can track it online with this CV if you want more information. I would like to, before talking about the specific vulnerability, just I would like to tell about common procedure in which I, like as a vulnerability researcher, is looking for vulnerabilities. When I looking at uh, and in this phase, what we have and what the steps that I'm going through is I have the binaries that implements the protocol, and I want to see how secure it is. So the most of the jobs that I will need to do here is, of course, reverse engineering, since the protocol is proprietary is and not documented. So no logic flaws can not be found online. So right here, I have my binary loaded into IDA, and I have some understanding of the protocol, right? Because I have analyzed it before. And now I'm ready to find actual vulnerabilities. So the first thing that I will go after is the logical ones, because logical ones are much easy to exploit than the memory corruptions. If after some time I cannot see, I go through all my attack vectors and I cannot see a possibility for a logical bug, I will go straight to the memory corruptions, of course. But since the exploitation of memory corruption is much more complicated, it OT system is still much easier, but it's not that easy to exploit in terms of time like logical bugs. So I'm straight going to find some logical flaws. And the main logical flows that I love to start with are pass reversal and command injection. Command injection are the flows that really easy to spot because they're use they are use a lot of strings in it, and only with eyes and just look at the strings table we can see some hints about the exploitability of this flow. So we found one common injection, and just a second, we found an OS common injection in this procedure. The procedure is called forced calibration. This is a command. This is the number of the command. As you remember, we have a command number in our header of in the protocol, and let's see how it's implemented. I It seems that I have another issue.
We are seeing you, right, Vera? Are
Yeah,
you listening? Yeah, yeah, yeah. Everything's okay. Only my cell phone that get
I
have
cannot.
internet.
It's not seems that I going forward with the presentation.
Okay, sorry.
It's okay.
Mas não tá bloqueando. Ela não tá conseguindo mudar. Check if you now it's working for you,
No,
please.
it's not.
It's not working.
No, I pressed next slide, and it looks like it's not moving forward. For me, it's not. It stays on the same page.
Né? Na verdade, apresentar de novo e botar de novo. Please, if you Vera, if you could remove the presentation and continue and put it again, maybe it
Yeah,
will work.
sure. Yeah, sure.
Sorry for
No,
that.
yeah, I understand that stuff
Yeah,
happens.
we are doing a live session. It's not so simple to do that, and the
Yeah, that stuff happen.
tem que apertar a minha.
Maybe if I present my screen, it will be better rather than the presentation.
Sorry.
If I present my screen, maybe it will be better rather than the presentation. I can share my screen. Maybe it will be better.
You are listeners. Bota a gente pra. You listen, Vera. We are trying to put you on the. I think that the presentation is not working so well. We are not
Okay.
seeing the presentation.
Maybe
Let's.
I can present my screen.
Yeah, yeah. You could do that.
Yeah,
Maybe it'll be better.
let's try that. Let's try that.
Yeah. Remove isso. Remove do palco esse daí. Desconecta esse aqui. Para isso aqui. Para ali com os três pontinhos. Expulsar do estúdio. Eita. Putz. Ela vai conectar. Só um pessoal. We could try again, Vera, please, if you could. Yeah, we remove you and try to put you again to see if it's working. I think now it's okay. You are only on mute. Try to unmute your. Okay, are you seeing now?
Yeah, you see the
Yeah,
presentation. Yeah,
yeah. I think everything now is
yeah.
okay.
Guys, for whoever stayed, thank you. It's for those who stayed, it's flattering. Seems that it's really interesting. So thank you very much for staying. So let's go to the command injection vulnerability that was found in the first calibration command of the protocol. And as I said, those vulnerabilities are somewhat easy to find relative to other vulnerabilities like memory corruptions. And why that is because we can look for system calls or some strings that will indicate that a bash call is executed. And you can see in this code snippet that this is exactly it. We see some command that is constructed in some way, and later it fed to system function which will execute in a separate shell the command that is uh, forwarded to it as an argument. So that's cool. And in our case, what we need to validate is whether um, we can as an attacker somehow to provide the input to that command. And in case of forced calibration, this is the only command that we found within the firmware that an attacker bypass can send to the device and be forwarded to the system library function. So this is how it looks like. This is how looks most of the command injection vulnerabilities. So we have some bash executable application, and we have the input that is controlled by attacker, and this is how uh, it is the command it looks like. And now for example, for a reverse shell, we only need to do is uh, instead of some files that will be opened by a candidate application, we provide a netcat application that will start the reverse shell, so it will be executed on the device. So here how it looks like, just with Python, we sending with a proprietary protocol that we have analyzed and know how it works. And we open the socket, and this specific command does not require any authentication, and we have our reverse shell on the device. So this was pretty cool. So we can start about anything else. I will. We don't have a lot of time, but there is something that I would really like to show you guys and girls. uh, there is something that we as researchers can understand only from reading the documentation, right? And I would like to showcase this example to you. We have here an instruction of erased administrator password, and here is what we can read from the documentation. We have the administrator password that can be reset by calling the support, and it cannot be reset by the support without a factory reset, which is and not a good practice, right? You wouldn't like to forget your password to call someone and it to call some support, and they will be able to reconstruct your password, right? Because if they can, maybe someone else can to do it as well, right? And this is what happening here. We are reading this documentation, and the red flag should be turned on in the head of security researcher. That something's very suspicious, because if the support technician somehow knows how to generate password, maybe its generation process is resides on the device itself. And long story short, it is we have ZCVE, um, and we do not have the actual time right now to go and see the actual implementation of it, but we do have a blog and at Claroty, and you are more than welcome to look at it and find more details. So I will just go forward with the actual technical details, and just show you this slide, which shows that the actual key that will with which the password will be reset is just a MAC address, which is not secret information. So if you have your hands on some device and you see its MAC address, which is written on the sticker on the device itself, you can log into it and bypass authentication. And this is how it looks like in the protocol, which the authentication is successfully bypassed. So we have our RC and bypass, which seems that this research was successful, and this is a great time to thank Emerson. So they patched the vulnerabilities promptly, and we enjoyed to collaborating with them, and they released a new version of the device that if for some reason you didn't update it, so go into it soon. So these vulnerabilities that were discovered during this research, and if you like our this research and the other ones, like I said, we have a blog with a lot of good stuff. And if you have any question about this one, you are free to reach me out in LinkedIn and GitHub or X. I would like to answer any questions. So that's it for my side. I was said that I have only 40 minutes. Guys?
Are you listeners?
LinkedIn. LinkedIn, give me your LinkedIn, please, Vera.
Let me. Tá falando aí, bota só, bota a gente.
Tá, tô falando aqui.
Vera, are you listeners?
Yeah.
Yeah. We have first they are requesting your LinkedIn. If you could share here in the chat.
Yeah, sure.
Yeah, and again, first, thanks for the great work that you're doing and you're present here for us. I think I have a question for you.
Yeah.
How many months or weeks that you work for this kind of that
Gas chromatograph.
that gas chromatograph research that you do?
How many weeks?
How many weeks or months that you work?
Okay, so this is a good question, because it looks like when you perform this type of research, the time it takes, it can somehow tell about time lapse of some other research, another device. This specific research was like 6 weeks, maybe 2 months, I think. The most of the research went to a emulation process, which is not an easy process. We didn't talk about it much, but there is a lot of dance to patching the binary, so it will be able to run on a simulation application like QMU and not the real device, and it take some time, and reverse engineering the protocol, which can also it's pretty tedious work if the binary is stripped. So I think it had been for 2 months, 2 months of work.
Perfect. And in a great work. Any questions? Vera, thanks a lot again for your support here in the team of 82 from Claroty.
I can hear you. Okay, guys, I'm gonna go, I think. This is, if you can, if you hear me in the presentation, this is my handle in all social media.
Oh, Vera,
It's okay.
sorry.
That's okay.
Yeah, we have an issue here in the internet that you are presenting, but we really would like to congratulate you, and we will move here to the next presentation, and the team that are here, all the
Thank you
attendants
very
are
much.
here. Okay,
Thank you. Bye bye.
bye bye. Thank you.
Agora eu já vi a apresentação aqui.
Sim.